Yes friends, welcome once again to the channel, and let's continue our discussion. So we will start with the coordinates of array, that is effect of translation. All these things I have already discussed in the previous class. Okay, so coordinates of array, that is effect of translation, that has also been asked to you in the year 2005. Okay, so this is suppose your paraxial ray PQ, and so this is your paraxial ray PQ, which is over here like this, from here till here. The ray which has been shown, that is your paraxial ray, and this is your x-axis. So angle is theta, and theta is the angle made by this line PQ with the x-axis, and alpha is the angle made by this same paraxial line PQ with the z-axis. Okay, with z-axis PQ makes angle alpha, with x-axis PQ makes angle theta. And suppose at this point the angle is alpha 1, at this particular point the angle is alpha 1, and at this particular point the angle is alpha 2. Okay, so what happens is that this paraxial ray is going like this. Okay, and the distance of this point P from this z-axis, distance of point P from this z-axis is x1, and distance of this point M from this z-axis is x2. Okay, so mm dash is x2, pp dash is x1, and this is your length basically. Okay, this is your length Q, and this is your T, means the distance traversed by this ray PQ from P to M. Whatever distance this ray traverses from this PQ ray, whatever distance this PQ ray traverses from point P up to the point M, that distance, when we take its z component, when we try to take its z component, it is equal to small t. Okay, so such is the situation with you. Okay, this question has been asked in 2005, by the way, so you must know how to solve this. So z-axis is the axis of cylindrically symmetric optical system. Your z-axis is the axis of a cylindrically symmetric optical system. This is your cylindrically symmetric optical system. Now what does it mean by cylindrically symmetric optical system? Cylindrically symmetric optical system just means that it is either convex lens or either concave lens. Okay, it is either convex lens, convex lens, or convex mirror or concave mirror. This is what is meant by your cylindrically symmetric optical system. Okay, this is the meaning of that. Consider a paraxial ray PQ in xz plane. So this paraxial ray PQ, this paraxial ray PQ clearly lies in the xz plane. Xz plane is the plane, this plane, which is the plane of your computer or mobile screen. Xz plane is the plane which is the plane of this computer or mobile screen, as you can see in the figure. Okay, as is evident from the figure. It is specified by its distance x from the axis. So this particular paraxial ray PQ is specified by the distance x from the axis z. Okay, so x are the distance. Do not get confused between this x and this x. Okay, this x is different and this x is different. Okay, this x is used for the axis, whereas these x are being used for coordinate along this axis. Okay, coordinates along this axis. So those are basically your x1 and x2, which are used to show the distance between z-axis and that particular ray at a particular point. Okay, And why these have been named as x1 and x2? Why these have been named as x1 and x2? Because these distances x1 and x2 lie along x-axis. That's why they have been named as x. Okay, because they lie along x-axis, that's why they have been named as x. So it is specified by distance x from the axis and the angle alpha it makes with axis. Okay, so the coordinates are described either by x comma alpha, or we can describe with the help of x comma lambda also, as told to you in the previous class. We can describe it with the help of x comma lambda also. Okay, so let's see. X changes as the ray proceeds. X changes as the ray proceeds in straight line in homogeneous medium. So let's see over here. X changes. Now this is a homogeneous medium, so PQ will be a straight line. Why PQ will be a straight line? Because the medium is homogeneous, as well as medium is also homogeneous, as well as medium is also homogeneous, and as well as it is of the same refractive index everywhere, and a single medium is there from here till here. Everywhere same medium is there, and also the medium is homogeneous, means the density does not change at any point. Whatever density it will be having here, the same density it will be having here. At every point the density is going to be the same, so uniform medium is there. Okay, so x will keep on changing. Okay, your x, that is the distance from z axis, it will keep on changing. Okay, this distance from z axis, that is your coordinates x, are changing, they are increasing as the ray is proceeding from P to Q. As the ray is proceeding from P to Q, the distance from z axis, which is equal to x, it is changing, it is increasing. Okay, so this is the thing. So x changes as the ray proceeds in a straight line in homogeneous medium. Okay, so x changes as the ray proceeds in a straight line in a homogeneous medium. The angle alpha does not, angle alpha does not change. So the thing written over here is angle alpha does not change. Why angle alpha does not change? Let us understand the meaning of this. Why the angle alpha does not change? The angle alpha is alpha 1 and alpha 2. For generality we have shown it by alpha 1 and alpha 2, but in reality the angle alpha, this angle alpha and this angle alpha, which have been denoted by alpha 1 and alpha 2, so alpha 1 will be equal to your alpha 2 over here. Why? Because this line PQ is a straight line. As this line PQ is a straight line, so these are basically this particular line which will be over here, those will be parallels. So this will be your transversal and these two will be your parallel lines. Okay, so just understand this thing, that this PQ will be your transversal and this will be parallel. So this angle will be alpha 1, this angle will be alpha 2, but both of them will be equal to alpha only. Okay, so this is the thing. Now so as the ray proceeds in straight line in a homogeneous medium, the angle alpha does not change. Let at point P, which is the point P, this is your basically point P. Okay, this is your point P. So let at P x equal to x1, alpha equal to alpha 1. Okay, so one subscript denotes point P and 2 subscript denotes point M. Okay, so you can see in the figure that the subscript 1 denotes point P and the subscript 2 denotes point M. Okay, so this is the thing. Now let at P x equal to x1, alpha equal to alpha 1. Okay, and at M x equal to x2, alpha equal to alpha 2. Then alpha 1 will be equal to alpha 2 by simple geometry. By simple geometry of two parallel lines separated by a transversal. okay, two parallel lines intersected by a transversal, by that phenomenon, we can have alpha 1 equal to alpha 2. I have already told you, you can see over here, okay, this alpha 1 and these two are your parallel lines and this is your transversal, okay. So alpha 1 will be equal to alpha 2. That clearly implies that those are basically your corresponding angles, okay. These two lines, you look at this line and this line, this particular line and this particular line, those are parallel, as both of them have been drawn parallel to z axis, so these will also be parallel, and this PQ is a transversal. Now this and this angle are corresponding angles, so that's why alpha 1 will be equal to alpha 2. So alpha 1 equal to alpha 2 is there because all this medium is homogeneous, so that's why PQ is a straight line. If this medium was not homogeneous, then what will happen? Suppose at this particular point the material has different density. At this particular point the material has different density. Suppose the density is continuously changing from here till here. If the density is continuously changing from there till there, then the ray will be bent, okay, the ray will not be straight in that case. If the density of the medium is changing at every point, then the ray will not be straight in that case. The ray will be either like this or either like this, okay. So the ray will be bent in that case, okay. Hopefully you got this, okay. So at m, x equal to x2, alpha equal to alpha 2, then alpha 1 equal to alpha 2, okay. The quantities x1 comma alpha 1 represent the optical coordinates of the ray at point P. Instead of alpha, we may also use the angle theta which the ray makes with the x-axis. Now, I have already told to you in the previous class that there are two types of representations. There are two types of representation of the coordinates. One of the representation is like your Cartesian and polar, okay. In your Cartesian coordinates we have x comma y as the coordinates, and in your polar coordinates what do you have? We have r and theta as our coordinates in the polar form, and r comma theta are in polar form, x comma y are in Cartesian forms. So these two are two different ways. X comma y and r comma theta are two different ways to represent your coordinate system. One is polar and another is Cartesian. Similarly, we have two ways over here. One is in terms of x and alpha, and another is in terms of x and lambda, okay. So these are two ways of our representation of coordinates of a ray, incident ray. So coordinates of an incident ray may be represented in two forms. One of the form is x comma alpha form, and another form is x comma lambda form, okay. The quantities x1 comma alpha 1 represent the optical coordinates at P. Instead of alpha, we may also use the angle theta which ray makes with x-axis. Then we have in that case alpha 1 lambda 1 equal to n1 cos theta. Now what is this theta? Theta is the angle which this ray makes at any point. Suppose at point P we are taking the coordinates, then whatever angle this ray PQ makes at point P with this x-axis, that will be theta. Similarly, the x-axis will be like this over here. Whatever angle this ray PQ makes with this axis, that will be equal to your theta. And both these are going to be equal. Both of these are going to be equal. Both of these will be with theta. This will also be theta, and this will also be theta only, okay. Because these are basically your parallel lines and PQ is your transversal. And also because alpha 1 equal to alpha 2, so this angle between this and this is 90 degree. This is alpha 2, so this will be your theta 2, and theta 2 plus alpha 2 will be equal to 90 degree. Both will be complementary angles. Similarly, this and this line, this angle is alpha 1, this angle is theta 1, so theta 1 plus alpha 1 will also be equal to 90 degree. And alpha 1 is equal to alpha 2, so theta 1 will also be equal to theta 2. Another reason is that, another explanation of this is that this and these are your parallel lines, and this angle is the corresponding angle, and this is the transversal. Okay, so that is also an explanation behind theta 1 equal to theta 2. So instead of writing theta 1 equal to theta 2, we will represent it simply by theta. Okay, over here also instead of alpha 1 and alpha 2, you may represent it by simply alpha. No problem at all. Okay, no problem at all. You can represent it like that also in this particular case, because the ray PQ is a straight line over here. Why it is a straight line? Because it is a homogeneous medium. Okay, so the quantities x1 comma alpha 1 represent optical coordinates at P. Instead of alpha, we may also use the angle theta which the ray makes with x-axis. Thus we have lambda 1 by definition. This is by definition. Okay, this is by definition. This is by definition. So by definition, lambda 1 equal to n1 cos theta, where lambda 1 is the optical direction cosine. What is this called as? This is called as optical direction cosine. Okay, this is called as your optical direction cosine. Okay, this is your optical direction cosine. So lambda 1 is the optical direction cosine of the ray. Lambda 1 is the optical direction cosine of the ray at point P. So at this point P, the ray will have x1 comma lambda 1 as the coordinates. At this point M, the ray will have x2 comma lambda 2 as the coordinates. Okay, so that is the thing. So lambda 1 is equal to n1 cos theta, lambda 1 optical direction cosine, n1 being the index of the medium, refractive index of the medium. Being the index of the medium means refractive index. We are talking about refractive index. Okay, so we are talking about refractive index. So optical coordinates of the ray at P may as well be expressed as lambda 1 comma x1. So optical coordinates of the ray at P, instead of x1 comma lambda 1, I have written lambda 1 comma x1. There is no difference at all. Either you write lambda first or you write x1 first. It doesn't make any difference. Okay. Effect of translation or translation matrix. So let us understand this effect of translation or translation matrix. From the figure which we have over there, which figure? From this figure, from this particular figure. Just do one thing in this figure, that extend this line up to here. Okay, so this will be your 90 degree, and this particular figure you will have to take out from here. Just take this figure out from here. Okay, this is your line, straight line. Okay, so extend this line up to here, name this point as M double dash, and take this figure out of the box. Take this figure out of the box, and when you take this figure outside from here and redraw it, it will look something like this. Okay, when you redraw the figure. So this was your ray PQ which was going up to here. Here was point Q, over here there was lens. Okay, all those stuff was there. So this figure is a part of that particular big figure, that complete figure. Okay, so this is your x-axis, this will be your z-axis along this. Okay, somewhere here it will be z-axis. So these are parallels. Okay, so this is your alpha 1, and similarly like this it will be over here also. Over here also this will be your x-axis extension, this will be your PQ extension, and this will be your z-axis extension. So this will be your again alpha 1 only, which is equal to alpha 2, and this will also be equal to your theta only. Okay, and this is also equal to your theta. Okay, so from figure x1 equal to pp dash. So clearly pp dash equal to your x1, x2 equal to your mm dash. So m dash, this is your equal to x2 as shown in the figure. Okay, let p dash m dash equal to t, and let this p dash m dash will be equal to your t. Why we have denoted it by t for translation. So p dash m dash equal to your t. Now this is a rectangle. By geometry this is a rectangle, so this will also be equal to t. So as p dash m dash equal to t, so x1 m double dash will also be equal to t only. Okay, not x1 m double dash, p m double dash. Okay, p dash m dash equal to t, so p m double dash will also be equal to t from geometry, because this is a rectangle. Which thing is a rectangle? p dash m double dash. This quadrilateral p dash m double dash, this particular quadrilateral is a rectangle. By geometry you can see this thing very clearly, because all the angles are 90 degree. So these opposite sides will be equal, so this will also be equal to, this is equal to t, so this will also be equal to your t only. Okay, so p dash m dash is equal to t, the translation of the ray. Okay, the translation of the ray, this t, small t is your translation of the ray. So x2 is equal to x1 plus t tan alpha 1. Now how this expression has come, let us understand. How this particular expression has come, let us understand. This as this is a rectangle, so this is equal to x1, so this will also be equal to x1 only. So this is also equal to x1. Over here, from here till here, this is equal to x2. So this will be equal to what? This particular thing will be equal to x2 minus x1. Okay, so x2 minus x1, when we take this to the left hand side, what will this be equal to? Okay, let us understand this very properly. Your m dash will be equal to what? m double dash, from the figure you can see this very clearly, plus m double dash m dash. This is the thing, okay, which you can see from the figure. Now let us have a look at this triangle. You know the definition of tan alpha. What will tan alpha be equal to? Tan alpha 1 will be equal to m double dash divided by p m double dash. Now you know this very well, that m double dash and this pm double dash is equal to small t, so it will be equal to small t. So your m double dash is equal to t tan alpha 1. Okay, this is the value. Now over here x2 is for m dash. Okay, so m dash, and your x1 is what? M dash m double dash. X1 is what? M dash m double dash, and this t tan alpha 1 is equal to your m double dash. Okay, so I have written nothing but this equal to this plus this. This is what I have written. Okay, so x2 equal to x1 plus t tan alpha 1, and as this ray is paraxial ray, so tan alpha 1 will be equal to your alpha 1 only, because the ray is paraxial. So you know this very well, that when angle is small, when theta is very small, approximately equal to 0, means theta is tending to 0, not exactly equal to 0 but tending to 0, means theta is a small angle. When theta is a small angle in radian, when theta is a small angle in radian, then tan theta is equal to approximately equal to theta, sin theta is approximately equal to theta, and your cos theta is approximately equal to 1 in that case. Okay, so by taking all these considerations, as your ray is paraxial, as your ray PQ, which you have over here you have lens, over here you have Q, so this is your paraxial ray, so this will be very small angle. although we have shown it to be a large angle over here, but this angle will be very small. Okay, so this particular angle is equal to alpha 1 and here alpha 1 is very small, so tan alpha 1 can be written as simply alpha 1. So that's how equation 1 has arose. Okay, that's how equation 1 has arose. As alpha 1 is a small angle for paraxial ray, over here it is written also in terms of lambda. Now what does it come out to be in terms of lambda? I already told you that lambda 1, what is the value of lambda 1? Lambda 1 is equal to n1 cos theta 1 and lambda 2 is equal to your n2 cos theta 2. Now you know this very well that theta 1 is equal to what? What is the value of theta 1? n1 cos 90 minus alpha 1. Okay, and similarly your theta 2 is 90 minus what is this? Alpha 1. Okay, 90 minus alpha 2, sorry. Now alpha 1 is equal to your alpha 2. Alpha 1 is equal to alpha 2. So theta 1 will also be equal to theta 2. So those are the considerations. So this is basically your theta 1, this is basically your theta 2. Okay. And you have put those values. From the figure you can clearly see this thing. This is your theta 1. Over here also, what do we have over here? Over here, this is your x-axis, this is your z-axis, this is your, so this is your alpha 2, this will be your theta 2. Okay, so alpha 2 plus theta 2 is again 90. So you have all this stuff. n1 equal to cos 90 minus alpha 1, n1 sin alpha 1. Okay, although we take the angle in radian, so this will be your pi by 2. Just make a correction over here. You should write, instead of writing 90 minus, you should write pi by 2 minus. Okay, instead of writing 90 minus, you should write pi by 2 minus. Why? Because this approximation sin theta is approximately equal to theta and tan theta is approximately equal to theta. When theta is very small, that is theta tends to 0, this applies only when, and cos theta is approximately equal to 1. These approximations apply only when theta is taken in radian. Okay, these approximations apply only when theta is taken in radian. So that's why writing 90 over here is wrong. You should write pi by 2 because the 90 degree is pi by 2 in radian. So you should write pi by 2 instead. Okay, so make a correction over here, just write pi by 2 over here instead of 90. So write pi by 2. So lambda 1 equal to n1 cos 90 minus alpha 1, n1 now cos 90 minus theta is equal to sin theta. You know this very well that cos 90 minus theta is sin theta. So 90 minus alpha 1 will be sin alpha 1, and as sin theta is approximately equal to theta for theta very small and alpha 1 is very small because it is a paraxial ray. So sin alpha 1 will be equal to alpha 1. Similarly lambda 2 equal to n2 alpha 2. So these are your equation 2 and 3. This was your equation number 1 and these are your equation 2 and 3. Okay. As n1 equal to n2. As n1 equal to n2 and alpha 1 equal to alpha 2. Now you know this very well that we have taken a homogeneous medium. So n1 will be equal to n2 because we have taken a homogeneous medium. So the refractive index does not change from point to point. We have taken a homogeneous medium, na? So that's why the refractive index remains same everywhere. Here, 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 or here, or over here also, at Q also, everywhere. Okay, everywhere the refractive index is going to be the same because we have taken a homogeneous medium. So what will happen? Your n1 is equal to your n2, alpha 1 is equal to your alpha 2. Because of this arises. Alpha 1 equal to alpha 2 arises because the medium is homogeneous. So PQ remains a straight line. That's why alpha 1 equal to alpha 2 arises. Okay, so lambda 1 is equal to your lambda 2. So this is your suppose equation 4. Now write this expression write this expression lambda 2 to be equal to 0 into x1 plus 1 into lambda 1. Write it like this. Why are we writing like this? You will understand. So this is your equation number 4. This particular equation written in blue pen. Okay, this is your equation number 4, and this is your equation number 5. Okay, by using this equation 2, how we have obtained equation 5? By using equation 2 in equation 1. Equation 2, just put out the value of alpha 1 from equation 2. Alpha 1 is equal to your lambda 1 by n1 from equation 2. Put it in equation number 1. Put this value of alpha 1 in equation 1. So as soon as you put the value of alpha 1 in equation 1, lambda 1 by n1 will come. Okay, so this is the expression which you get finally, which is equation number 5. Okay, so equations 4 and 5 may be written in the matrix form. Now how do we write in the matrix form? Let us understand how do we write in the matrix form. So we have something like this with us, that 0 into x1 plus 1 into lambda 1. Okay, so this and these equations just write like this: lambda 2 on the top, and correspondingly we have x2. So x2 at the bottom will be equal to the coefficients. What are the coefficients? Coefficients are 0, 1, 1, t by n1. So it will be 0, 1, 1, t by n1. Okay, and over here we have x1 and lambda 1. So lambda 1, x1. Okay, so this is the thing. So you will understand this more clearly. Okay, so whenever you must have learned this thing in your lower classes, that whenever you have an equation of this kind, okay, that y is equal to mx plus m1x plus m2x. This is your equation number 1, suppose. This is your y1, suppose, and suppose you have y2 equal to m1x. Suppose we have, let us understand this more clearly, y1 equal to m1x1 plus m2x2, and y2 equal to m3x1 plus m4x2. Suppose we have something situation of this kind, then how do we write the equation matrices? We write the matrices like this, that this is your y1, this is your y2, that these and these are written upside and down. This will be equal to m1, m2, okay, m1 and m2 side by side. Then we have m3 and m4, so m3 and m4 side by side, multiplied by this x1 and x2 in the up and down. Okay, so this is the thing which you have to practice and understand. So equations 4 and 5 may be written in the matrix form like this. Okay, in this form. This is your equation number 6. Now when you know the matrix rule of multiplication. Do you know the matrix rule of multiplication? You must be knowing. So lambda 2, so we will write lambda 2 equal to, we will write, because over here it is equal to. So multiply this row by this column. So what will come? 1 into lambda 1 plus 0 into x1. Okay, similarly this row will be multiplied by this column. So x2 will correspond to this multiplied by this. So what will happen to x2? x2 will be this multiplied by this, and lambda 2 will be this multiplied by this. Okay, so x2 will be equal to t by n1 lambda 1 plus 1 into x1. Okay, 1 into x1. So you know the matrix rule of multiplication hopefully. Lambda 2 equal to this multiplied by this. Okay, so term by term we go. We multiply this by this by this. Okay. So and when we try to find out x2, this multiplied by this will happen. So this will go with this will go with this. Okay. So such is the thing. And over here this upon sign must not be there. Over here there is a misprint. Okay, there is a problem over here. Over here I have written upon type of symbol, but there should not be any upon symbol. It is simply lambda 1 x1. Okay, there is no upon symbol over. Just cut this over here. Just cut this. Okay, so there is no upon symbol. Just ignore that symbol. Over here also accidentally I have written upon symbol. Over here also accidentally I have written upon symbol. Just cut those symbol. Okay. So these are what? These are equal. These are basically your like this. Okay, without any upon sign. And this is basically your like this without any upon sign. Okay. So this is your equation 6. Column matrices. These are basically your column matrices. Now let us understand why are they being called as column matrices. Suppose you have a matrix of this kind. This is a row matrix. Why this is a row matrix? Because every matrix has like this. This is your row, first row. This is your second row in this matrix. Okay. And similarly, this is your first column, this is your second column in your matrix. Look at it once again. This is your first row, this is your second row in this matrix. This is your first column, this is your second column in this particular matrix. Okay. So what is a row matrix? Suppose I have 1, 1. Suppose 1, 1 I have. This is your row matrix. Okay, because only one row exists in this matrix. But suppose I have only a column with me. 1, 2. This is what? This is a column matrix because it has only a column. Okay, so over here, these are only vertical. Only one column is there. So this lambda 1 x1 will be a column matrix. So lambda 1 x1, this is a column matrix, and lambda 2 x2, this is a column matrix. And is this a row matrix or column matrix? So this is neither a row matrix nor a column matrix. It is a 2 cross 2 matrix. It is a 2 cross 2 matrix. It is neither a row matrix nor a column matrix. It has 2 rows and 2 columns. So that's why it is a 2 cross 2 matrix. This matrix is a 2 cross 2 matrix. Okay. So this is the thing you have to take special care about. So column matrices, over here this upon sign is not there. This has been put accidentally. So just ignore it. Okay. So column matrices lambda 1 x1 and lambda 2 x2 may be looked upon as the rays at P and M. So I have already told you that your lambda 1 x1 comma lambda 1 where the coordinates of point P, and x2 comma lambda 2 where the coordinates of point M. I have already told you. So the matrix corresponding to point P will represent the ray at point P. So this represents your ray at point P, and this represents your ray at point M. So let us understand this from the figure. Okay, let's go to the original figure. The coordinates of this point P were x1 comma lambda 1, and coordinates of this point M are x2 comma lambda 2. Okay, so the matrix corresponding to this point P is lambda 1 x1, and matrix corresponding to this point M is lambda 2 x2. Okay, so these column matrices, this column matrix lambda 1 upon x1, not upon lambda 1 x1 column matrix. This represents your ray PQ at point P. This particular thing represents your ray PQ at point P. Okay, and lambda 2 x2, this particular thing represents your ray PQ. This represents your ray PQ. This particular thing represents your ray PQ at point M. Okay. So column matrices this and this may be looked upon as the rays at P and M. Okay. The effect or the process of translation over a distance t in a medium of index n1 is given by 2 cross 2 matrix. Now you clearly, this is the point P and this represents your point M of the ray PQ. So the ray PQ, in the ray PQ, over here at Q the length is there, over here at P the point is there, and from point P to point M there has been a translation. Why there has been a translation? Because the ray has travelled from P to M. Okay, the ray while travelling from P to Q, has first travelled from P up to M. Okay, so from P to M it has travelled. So when it has travelled from P up to M, so this is the matrix which represents it. So when at point P I apply a matrix of this kind, I get the matrix at point M. So this is your translation matrix, because from point P to point M the ray has travelled. So when I apply at point P this translation matrix, I get the matrix at point M. So this is basically your translation matrix, because point P and M represent your translation. Okay. The effect or process of translation over a distance t, when the translation is happening in a medium of refractive index n1, is given by 2 cross 2 matrix like this. This is your equation 7. Translation or transfer matrix. You may call it either translation matrix or you may call it a transfer matrix. Okay. It transforms the ray lambda 1 x1 into ray lambda 2 x2. Now it is obvious that determinant of this will be equal to 1. Now how to find the determinant of a matrix? Suppose this is the matrix you have, then the determinant is found like this: 1 0 t by n1 and 1. So when I replace these curved brackets, with a vertical line, just replace these curved brackets with a vertical line. So one vertical line over here, one vertical line over here. So what happens is that it becomes a determinant. So when it becomes a determinant, what happens? This multiplied by this. Okay, so 1 into 1 minus this multiplied by this. So 0 into t by n1. Okay. So this is the thing which you get. So in this way determinant is found for a 2 cross 2 matrix, and you don't have to worry for it. Because beyond 2 cross 2 matrix nothing will be asked to you. 3 cross 3 matrices will not be asked to you. Okay. Although 3 cross 3 matrices might also be there, but it will require a thorough knowledge of mathematics for it. For a 3 cross 3 matrix, what is a 3 cross 3 matrix? Suppose I have a matrix of this kind. This is a 3 cross 3 matrix. Why this is a 3 cross 3 matrix? Because 3 rows are there and 3 columns are there. So that's why this is a 3 cross 3 matrix. But in your examination, never a 3 cross 3 matrix will be asked, because in case of a 3 cross 3 matrix you require thorough knowledge of mathematics, and your mathematics is not an optional for you. Okay, so you need not worry about it, that 3 cross 3 will be asked. Never it will be asked, never in your examination. Only up to 2 cross 2 only it will be asked. So now it is obvious that determinant of t equal to this. So it is equal to your 1 basically. How we have found out? This multiplied by this, 1 into 1 minus this multiplied by this, 0 into t by n1. So 0 into t by n1 is 0. So 1 into 1 minus 0 equal to 1. Okay. So this is your equation number 8. This is what? This is your equation number 8. Now, if the gap T be divided into two adjacent gaps T1 and T2. Now suppose I divide this gap T. Suppose I do one thing, that this is your gap T from here till here. This is your gap T. But I suppose divide this into two gaps T1 and your T2. I divide it like this, okay, where your T1 plus T2 is equal to your capital T, small t, okay, without subscript T is equal to T1 plus T2. So in that particular case, what will happen? One more line will come over here, one more line will come over here, okay. So what will happen in that case is that, suppose this is your T1 and this is suppose your T2, and suppose this is your point. So you have drawn it like this, and suppose you have drawn it like this. So what will happen? The thing which will happen is that this will also be equal to your alpha only, okay. So everything can be applied similarly. So in that particular case, I will not go into the derivation of that. It is very easy to understand from common sense, okay, from common sense. If gap T is divided into two adjacent gaps T1 and T2 having the same index n, again the refractive index has been taken as the same, which is equal to n, we get two successive translation matrices, okay. Instead of just consider, just only thing is that instead of this T, I have suppose over here T1, okay. So what happens? Instead of this T, I will have T1 everywhere in my expression, okay, and this is your T2. So instead of this T, we will have T2 over here, because this is the similar case. From here the ray will start, okay. So if the gap T be divided into two adjacent gaps T1 and T2 having the same index n, we get two successive translation matrices. T1 equal to this and T2 equal to this. These are the two successive translation matrices, okay. It can be checked. Now it can be checked. How it can be checked? This particular thing can be checked. T1 T2 equal to T2 T1 equal to this much, and this is equal to T, which is equal to this much. How we have over here put an equal sign, okay, over here. I have missed it, but you have to put one equal sign over here also, okay. So how we can check this? Just apply the matrix rule of multiplication. Just write these two matrices side by side. Just write these two matrices side by side. So I write them side by side. Okay. Now just multiply term by term. This row will be multiplied by this row. The result will be written over here. Then this row will be multiplied by this column. The result will be written over here. Then this row will be multiplied by this column. The result will be written over here. Then this row will be multiplied by this column. The result will be written over here, okay. So you can write it. So this row multiplied by this column, the result will be written over here. Then this row multiplied by this column, the result will be written over here. Then this row multiplied by this column, the result will be written over here. Then this row multiplied by this column, the result will be written over here. And if you do that, this multiplied by this, okay, so 1 into 1, I am writing the first expression. And then this multiplied by this will be equal to 0, so I am writing 0 over here. Then this multiplied by this will happen, so 0 plus this multiplied by this will happen, plus 1 will come, okay. So I have got clearly over here, instead of this I will write 1, over here instead of this I will write 1, okay. Then we have this multiplied by this, so T1 by n So what will happen? These two expressions you had already written. Then this multiplied by this will happen. So T1 by n plus, so T1 by n plus this multiplied by this will happen. T2 by n will come. Okay. Then this multiplied by this will happen. So 0 will come, plus this multiplied by this will happen. So plus 1 will come. Okay. So ultimately you will get the expression like this. You can either check T1 T2 or either you can check T2 T1. Both are going to come out to be the same. Both are going to be the same. So this is the thing which you will get. Okay. And over here I have forgotten the equal to sign. You can represent this product by capital T and it will be equal to like this. Okay. So we have divided into two parts. That's why T1 plus T2 has come. We have divided into two parts. That's why T1 plus T2 has come. Instead we could have divided into many parts. Okay. We could have divided this particular space into three parts also. We could have divided. So this will be your T1 part, this will be your T2 part, this will be your T3 part. In that particular case, this thing will apply. Which thing? This particular thing will apply in that case. Summation or Ti by n. Okay, this thing will apply. So all the translational matrices can be multiplied to produce a single matrix for the effect of the whole gap. Okay. So all translational matrices can be multiplied to produce a single matrix for the effect of whole gap. Okay, so let us understand the meaning of this. All the translation matrices. So all the translation matrices. Okay, like this, T1 was a translation matrix. Okay, T2 was a translation matrix. So all translation matrices can be multiplied together to produce a single matrix, which is a single matrix. Now T1 plus T2 equal to your T, total gap T. Okay. So it can be used to produce a single matrix for the effect of the whole gap. Okay. So your T1 plus T2 is equal to your T. You have divided this area. You have divided this particular area into two gaps. This is your T1 gap and this is your T2 gap. Okay. So the effect of translation from this to this, that is by the T1 matrix. Okay. That is shown by the capital T1 matrix. Effect of translation from over here till here, that is the small t2 translation, that is shown by capital T2 matrix. When we multiply them together, what happens is that we get the translation matrix for the whole thing, and the whole distance is T1 plus T2 equal to small t. So that can be represented as capital T. These and these are multiplied together to produce capital T. Over here it is addition. In the case of distance, it is addition, but when we try to think about it in terms of multiplication, in terms of matrices, then it becomes multiplicative. In terms of distance, it is additive. But when we convert it into translation matrix, it becomes multiplicative. Okay. So that's the meaning of this statement. So all the translation matrices. So we can have more than two gaps also. Okay, we have more than two gaps also. For example, we have three gaps. We have four gaps, suppose. T1, T2, T3, T4. Then what will happen? T1 plus T2 plus T3 plus T4 will be equal to your capital T. Small t. But your matrices, when we try to write in terms of matrices, so corresponding to T1, we will have capital T1. Corresponding to T2, we will have capital T2. Okay, all these will be multiplied. Corresponding to T3, we will have capital T3. Corresponding to T4, we will have capital T4. All these will be multiplied to give you capital T, which corresponds to this small t. Okay. So in terms of matrices, it becomes multiplicative. So all the translation matrices can be multiplied to produce a single matrix for the effect of the whole gap. Okay. Now the refraction matrix we will do in the next class. The refraction